Wouldn't you love to be able to fly? In the world of Disney logic, Dumbo can fly because he has very large ears. We invited a NASA engineer to explain what it would take to get that elephant into the air and when we can expect to get our jetpacks. Up next on Science Goes to the Movies. Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Lisa Beth Kovets. Disney rebooted Dumbo, its saddest cartoon ever. And lots of stuff has changed from the 1941 version, but still in the center of the story is a flying baby elephant. Today, joining us is Professor Mason Peck, currently at Cornell University and formerly the Chief Technologist at NASA, and he is going to explain the seriousness behind the silliness of airborne elephants. Professor Peck, welcome.
It's great to be here.
In the movie, Dumbo can fly because of a magic feather, but in real life, things fly when something called the lift equation says that they can. Professor Peck, for those of us who don't speak math, what does the lift equation say?
It says that the faster you go, in principle, the better you can fly. So the equation that's at stake, if you'd like to hear the equation, is the lift force is 1/2 times rho v squared CD A. All right, so 1/2 we understand. Rho is the density of air, v the velocity squared. So again, the faster you go, the more lift force there is. CD is the coefficient of drag, and area is the area of the wing. So put all this stuff together, and you have an equation that pretty accurately describes how much force can lift up an aircraft or maybe an elephant.
Engineers have made it possible for amazingly big and heavy machines to fly, so why not an elephant? And using the lift equation, the internet has concluded that if Dumbo was a baby elephant weighing about 600 pounds, he would need a wingspan, or in this case an ear span, of about 19 feet. He would need to maintain a velocity of 200 miles per hour to keep airborne, and everything really would be so much better if his ears were not in the ear place, but further back towards the center of his body. Now, is the internet out of its collective mind, or given the right circumstances, could an elephant fly? And if an elephant can do it, why not us?
Yeah, well, if this unfortunate elephant with his ears on his rib cage ever were to try to fly, he'd encounter a couple of other problems. One of them is just the strength of the material that an elephant's made of. You know, it's flesh and bone like we are, skin, a little bit of hair. Those are not really the materials for supporting an aircraft, let alone an elephant, because what we need is something stiff. It can't be like the elephant's ears or his trunk flapping around in the breeze. It's got to be stiff enough to withstand the loads, right? It's got to be strong enough not to fail. There's a lot going on here, and just the musculoskeletal implications of having wings are why birds are shaped the way they are and why elephants are not shaped like birds. So this idea that elephants could fly, I think you have to say, by some simple math, sure, but not necessarily everything is going to all come together. You know, there are other reasons why elephants would have trouble flying. You know, how a bird navigates, how it exploits its body to change direction, that's also part of the story. Birds, their entire body moves to change how it flies, how they fly through the air. An elephant doesn't have the kind of tail that can direct its motion, right? So Dumbo has some special skills, apparently, that he can change direction and swoop and fly. That's not likely.
So the lift equation tells us how we can get up, but then how we move around is a whole other elephant, a whole other ball of wax, a whole other thing.
Yeah, that's true. So if you think about a typical aircraft, airplanes have control surfaces, they're called, little flaps on the wings or on the tail or on the rudder, the vertical stabilizer. All these moving parts allow the airflow to get adjusted. The pilot can move things around and change the interaction between the air and the airplane. I suppose if Dumbo's particularly clever, maybe he can learn after some practice with the magic feather just how to move legs and trunk and other things to re-vector how the flight happens. But yeah, there's more to it, unfortunately, than just lift. So lift equation tells us how much force you'll get when you travel a certain speed. But it's not the only way to fly. There's actually two other ways. Another one is flapping. So people have tried making ornithopters, they're called, flapping wing aircraft. And that flapping motion is an entirely different thing. You don't have to travel fast, but you do have to displace air in large quantities. Maybe Dumbo could do that too.
So what about the dragons in Game of Thrones? Have you seen the way they move the way a classic dragon moves in any other movie? Is that within the ballpark of valid way for a beast of that size to move?
Yeah, all dragons I'm familiar with are very successful in flying this way, sure. It's just like a bird or a bat, right? The idea is that by extending and moving the wings and gathering up a large volume of air and pushing it, the wings are displacing air, displacing momentum is really what's going on. The force that acts one way on the dragon is going the other way on the air. So to have something to push against is really what it's all about for that kind of flying. For the lift equation type of flying, where you just have to be going fast, it's a totally different story. Here, for Dumbo, let's say, if he's traveling in a steady level flight, they call it, the air moving over the top of the wing has to be traveling faster than the air going under the wing. When that's the case, I know, right? When that's the case, because the air is traveling faster above, it's got to be less dense. And when it's less dense, it represents a difference in pressure, and that pressure lifts up. That's a very complicated combination of effects. And in some respects, just the flapping idea is way simpler, which is probably why in the old days people tried to build flying machines that flapped. It made sense to them.
Yeah.
But thanks to the 19th and 20th century, we now understand this principle, the Bernoulli Effect and other things that tell us why wings work the way that they do. But I guess what I'm saying is that the problem of how you even stay up in the air is one interesting area to think about. A whole other area is how do you control where you're going. Just being able to go in a straight line is all well and good. Dumbo's got to do a lot more.
Dumbo's cute, but let's talk spaceships. The Soviets got into space on October 4th, 1957 with Sputnik. The Americans were a little less than a month behind with the first Mercury launch. And then, on September 8th, 1966, Paramount Pictures launched the first Star Trek series, and viewers got to fly across the galaxies in the USS Enterprise week after week, episode after episode. And Ensign Pavel Chekhov had absolute control of the ship's movement at all times because all fictional pilots can maneuver their crafts through asteroid belts or execute high-speed 180-degree rotations. But in real life, how do you steer a spacecraft?
Spacecraft usually, at least the ones we build now, usually don't have much more propellant than just barely necessary to squeak by on their various interplanetary trajectories. So when a spacecraft changes direction, it's usually thanks to gravity, the gravity of the Earth, the Sun, Moon, wherever that the spacecraft might be going. It is true that a spacecraft can turn, and that's called attitude control. So we think of attitude as maybe your personality or something like this, but in fact it's, for spacecraft at least, it refers to the orientation, the tilt of the spacecraft. Attitude control, you could use thrusters for it. You could have other little tiny rocket engines that push against the spacecraft and rotate it. But the better way to do it, the way that does not consume any propellant, is to use internal motion, by which I mean, for example, a wheel. Say I am holding onto a wheel in space and I turn it one way, I turn the other way by what's called conservation of momentum.
Right.
So now if I have three of these wheels, I can imagine turning one this way, one that way, one this way, and I can get a torque or a change in momentum in any of three directions I could care about. That whole process of attitude control is what makes spacecraft capable of pointing at the Earth or pointing at Mars and doing their job. That pointing problem, that attitude control problem, doesn't really help you move anywhere. Like I say, it's the motion of a spacecraft toward a planet or anywhere else is pretty much all governed by gravity. It takes a lot of energy for a spacecraft to leave the Earth. And compared to the rest of its voyage, most of the energy of a spacecraft really gets spent in the first few minutes as the rocket lifts off of Earth and maybe as the spacecraft leaves a planetary environment. After that point, you're lucky if a spacecraft can change its velocity a tenth of what was necessary to get off the Earth.
Really? And what about returning to Earth? Does that take a lot of energy also to come back down?
You have to somehow get rid of all the energy you added. So as a spacecraft comes back to Earth, it enters the atmosphere probably at high velocity, and that means one of two things. Either you got to just put up with it, let the spacecraft get hot the way that the space shuttle did, and then let it cool off later, or in the case of some other vehicles, you burn a surface away. It's called ablation, a heat shield that could get super hot also just ablates and moves the heat away through burning ash. It's a very energetic and difficult thing to do, to the point where, in fact, the air around the space shuttle, or even a capsule for humans, gets so hot it turns into a plasma, like a candle.
Really?
The flame on a candle is,
Yeah,
in fact,
sure.
a plasma. That plasma is conductive, like electrically conductive, and turns into a shield that prevents communications from traveling through the air. So there's a lot of complicated stuff going on there, and it's all we can do as humans to devise a system that'll survive atmospheric entry. It's really hard to do.
Wow. Wow. And what about docking? I mean, like in space, in all these movies, two spaceships just come alongside each other and they're docked. Is that an easy thing to do?
Docking in space is hard for many, many reasons. One of them is that on the ground we have lots of things to help us. We have gravity, which, despite that you might want to fly someday, is helpful in keeping things on the ground where they belong. So gravity helps steer a car. It helps keep things where they need to go. And the air and all the friction around us helps to slow things down. In the case of a spacecraft, none of that's there. So you have now 3 angular motions that are possible, 3 so-called translational motions, for a total of 6 individual degrees of freedom that you'd have to control as an astronaut. You know, it's hard enough to steer a car, right?
Right.
You really have 1 degree of freedom. Are you going left or are you going right? And maybe the forward, backward of the gas pedal. And then maybe that's 2. But an astronaut has to fly in 6 separate degrees of freedom. This is true for an aircraft pilot as well, but really an aircraft doesn't normally flip around in a complicated way.
Right.
At least if it does, you have other problems. In the case of a spacecraft, though, really it's all about simultaneously controlling all these different degrees of freedom. So docking is really hard. You want 2 things to find the same place in space when each one of them independently has 6 other things it would rather be doing. So mathematically it's quite a mess, and that's why usually for docking spacecraft, computers are involved.
The computer is the pilot?
So you might have a computer helping the pilot. You might also have people on the ground helping to steer these 2 together. When the space shuttle and the space station used to dock, there was a video camera basically that would show a target, and you try to match up the target as a pilot. Now that's in the last few feet or inches of motion where you got to get it right. But before that, for the hundreds and thousands of miles that might be necessary to get to those 2 points, the physics are really complicated. I don't want to say that they're so complicated it can't be done, because it's obviously done, right? But it's much harder than you would think. It's harder than in the movies.
And your lab is working on docking right now. What's your idea of how to improve docking?
Well, our idea is, first of all, to be as dumb as we possibly can. And think if you would just imagine what would be two things that like to come together in general. Magnets. Right? So yeah, the idea is magnets. Now, a problem with magnets is that, certainly permanent magnets of the type you might think of, like a piece of metal, like a horseshoe magnet, it's always on. If you want to dock, that's helpful. But what if you want to undock? Or what if you're close and you feel like maybe I want to dock later or dock a little differently? You'd like to be able to turn off a magnet, and how do you do that? So an answer might be, what about electromagnets? You know that you can put current through a wire and that forms an electromagnet, sure. But that takes a lot of power.
Oh.
So the question is, how can you turn on and off a permanent magnet? And our answer is, let's take 2 magnets, and when we don't want them to work, we point them toward each other and cancel them out. When we do want them to work, we can point them that way, or maybe that way, and we get a mechanical version of a magnet that can turn off and on. So that's the dumb as a bag of rocks idea that we have that seems to work pretty well. And if we're lucky, our lab will be able to launch this with NASA's help in another year.
Well, your dumb as a bag of rocks idea seems actually quite brilliant.
Well, I appreciate that, and I think that dumb is undersold sometimes.
Yeah.
Honestly, I think things that are simple, if no one's thought of them yet, it's a great idea. It's quite easy to think of very complicated solutions that no one's thought of, because maybe that's a good reason they haven't been thought of yet.
Right.
I like ideas that are simple enough to do the job, and yet they're new.
Right.
So I think it's a research success, let's say, to come up with a dumb idea,
Yes. Yeah,
believe it or not.
Yeah. In shows like Star Trek or the Orville, a lot of the ship's culture is based on nautical influences, as if space exploration rose up out of the Navy. And like seafarers of old, fictional spaceships use the stars for navigation. But spaceships are traveling much faster and much farther than any naval vessel ever did. At those distances and speeds, can a ship navigate by the stars?
I think absolutely it can, and in fact it probably has to. Near the Earth, let's say within our solar system, NASA's been able to communicate with spacecraft and send signals back and forth that help the spacecraft understand where it is. It's called ranging. And that works great. But we're finding out that the way in which it's probably more successful to navigate between stars, which no one's done yet, by the way, but if we needed to do that someday, we'd have to rely on sources that are not from Earth. Partly because, remember, the speed of light is a constant thing. It takes so long for a signal to go from Earth to some distance between the stars, it might take years, in fact, that we can't really use that reliably as a way of telling us where we are. So a spacecraft has to be able to navigate autonomously between the stars. To navigate autonomously with no help from the Earth, a spacecraft probably has to depend on what's around it, and about the only thing out there are the stars. If something like the Orville or the Enterprise are traveling really fast, one of the cool things that happens to what you see in the star field is the stars change color. Now this is a weird effect that has to do with relativity. As you, or maybe even just the Doppler shift, as you travel faster and faster, the stars coming towards you, their color shifts to the blue part of the spectrum, and the stars behind you shift to the red part of the spectrum. So if you know what star you're looking at, and you know what color it's supposed to be, more or less white, and then you can tell how red it's become or how blue it's become, you kind of know how fast you're going.
Wow.
But that only works when you're traveling really, really fast. So this is why I say it's a science fiction kind of a question. You have to be traveling maybe a tenth or even more of the speed of light, which right now nothing can do. So our grandchildren might be the first who will, no kidding, experience some kind of relativistic travel. Right now, we're not experiencing that. We're on the cusp, I think, of being able to send spacecraft beyond our solar system. And there's a lot to see out there. You know, there are extrasolar planets. We've discovered one that's near, or orbiting around the nearest star, which is Proxima Centauri. That's about 4.5, or a little less than 4.3 light years from Earth. A light year is the distance that light travels in a year, right? So that means if you were to travel there at light speed, it would take you 4.3 years to get there. And then if you send a signal back, it's another 4.3 years to get that signal.
Oh, right.
So it's a long and slow process.
Yeah.
And until we develop some completely other form of travel that violates this principle of speed of light, we are pretty well stuck within a few, I'm going to say, light years of Earth.
Well, let's talk about how we're traveling through the stars. As many of you already know, the USS Enterprise runs on dilithium crystals, which don't actually exist. But in the British show Red Dwarf, the JMC mining ship of the same name has something called the front ram scoop, and it fuels the ship by collecting traces of hydrogen to send to the ship's energy core, which was a real theoretical thing called the Bussard ramjet, proposed by nuclear physicist Robert W. Bussard in 1960 and funded by Bob Guccione through Penthouse magazine profits, but that is a whole other story. What we're getting at here is that neither of these ships, in fact, none of our favorite fictional space vessels, ever need to return home to refuel. And in real life, our guest, Dr. Peck, is working to make the return home fuel run a thing of the past by converting a truly ancient substance into rocket fuel. So what are you going to burn to make rocket fuel?
Our thought is, let's use the most common material out there that works as rocket propellant, and that's water.
What?
So water is plentiful all over the galaxy, as far as we know. It's certainly all over our solar system. It might be surprising.
But isn't the universe a dry, barren void?
The universe is wet. In fact, the solar system is wet. The moon, in permanently shadowed craters, so-called, has tons of water. It's in the form of ice, and it's been there for probably 1 billion years or maybe longer. There is ice on the moon, there's ice on Mars. In fact, Mars in particular, just a couple meters below the surface, there's a surprising amount of subsurface ice, which sometimes even flows as water. So water is really prevalent, and if you can make water work as a propellant, that would be what you'd like to use. So we have an idea of making that happen, and it's, by the way, not an original idea, but we've, I think, taken it pretty far. The idea is, let's start with the water, split it into its constituent molecules, hydrogen and oxygen. When you have those two molecules, they want to go back and become water. In fact, when you burn hydrogen in oxygen, you're making water. That is the way in which water came about in the first place, was combining oxygen and hydrogen. So we're going to go to a lot of effort, starting with water and ending up with water. But in the meantime, when it's a gas and combusting and flowing out of the rocket, that fluid, that rocket propellant, is what pushes the rocket forward.
So what happens to the original separated hydrogen and oxygen once the fuel is burned?
So we start with water, add sunlight, that separates it into the hydrogen and oxygen gas, and then we spark it with a spark plug or a glow plug and ignite it. it explodes, it detonates, and that explosion results in a bunch of really hot steam. So now the hydrogen and oxygen have become effectively steam. And at some point in the future, hundreds of miles away from our spacecraft, it'll become water again, and we'll never see it again.
Wait, so the further we get out into space, the closer we get to the steam engine?
Yes, it's a steampunk way of traveling in space. I like the idea that this is a technique that is very much the way that life works on Earth.
Yes, so this whole science, a lot of the things that you're suggesting sounds like they're coming out of some very natural, simple, basic reactions.
That's true for water, right? Water is all over Earth, of course, and life on Earth depends on sunlight. So it sort of makes sense to me, at least, that the combination of water and sunlight might be the future of space propulsion.
That's amazing. That's amazing. In Professor Peck's Water as Fuel project, the water is multitasking like crazy, dampening unwanted oscillations and acting as a heat sink. What are those two things that I just said? and in real life space travel, does everything have to be economical?
At the moment, we don't know how to launch spacecraft and fly spacecraft without saving as much mass as possible. We have to do that. It's mass is money, mass is time. There's a thing called the tyranny of the rocket equation, where in order to carry fuel with you, you've got to carry fuel to propel that fuel, right? So you're constantly chasing your tail, and there's only so much you can really do with propellant. So any mass you can save is a good thing. To answer your question, water on board a spacecraft, since you have it, might as well be used for other things. It might as well be used, for example, as a radiation shield. In space, there are high energy particles, there's cosmic galactic rays, there's a lot of things that can do the body damage. So we like to shield from that. Now, we could use aluminum for that, we could use tantalum, all sorts of other materials. But since we have water already, why don't we use that? In fact, specifically, why don't the astronauts live effectively inside a shroud made of water, inside the fuel tank, if you like?
Right.
That would be a great way of keeping the radiation out. And by the way, it's also convenient for keeping the temperature about right.
Which you could never do with a different kind of fuel.
Yeah, with other kinds of fuel, they're typically toxic. I mean, water got to be the least toxic fuel out there, right? They have something these days called green propellant, and it goes by various chemical names, and it's relatively non-toxic. They say only maybe about as toxic as coffee. I don't know about you. I'm maybe willing to drink coffee, not so much the rocket fuel.
Right.
So water, I'd be willing to drink, which means, by the way, the astronauts could also use the rocket fuel as drinking water.
Right.
So that's a neat feature, because if you think about how NASA needs to do things, how we all need to plan a complicated thing like a spacecraft mission, you need to have contingencies. Things may not go perfectly. So you want to have a little extra fuel, a little extra water, a little extra radiation shielding. But keeping track of all those separately means you have a lot of extra stuff that maybe you're not going to need. What if you just doubled up or tripled up on those things and have one source of extra resource?
On TV, Captain Kirk and Jean-Luc Picard are out in space exploring just to explore. In the Orville, Seth MacFarlane's crew is exploring and also patrolling, keeping space safe for other travelers. But what about us? Why do we go into space?
There's a lot of reasons we go to space. We could go to space to discover, right? That's science, let's call it. We discover new facts about the world around us, the universe around us. The fact that we know our sun's age, the fact that we know how quickly the universe is expanding, our understanding of maybe the future of our solar system is thanks to discoveries that we've made in space. Another reason to go to space is to make money. There are satellites up there right now that are sending broadcast information back to Earth. It's, I think, about a $14 billion a year industry sending data to and from space.
Wow.
In the future, making money in space could mean mining asteroids or mining the moon. We're not doing that now, but that could be a thing. And the other reason, of course, is exploration. So I'm going to distinguish discovery from exploration. When we discover, we're discovering maybe through robots like the Mars rovers. Exploration, to me, is about humans and boots on Mars or boots on the moon. There is something in us as humans that make us want to be present in the place. We want to see the moon. We want to pick up the moon dust. We want to hold that Mars rock in our hands. We want to look under that object on Venus, if we can maybe send people there someday. We want to be the people in place. Yeah. Steve Squyres is an astronomer, a planetary scientist. He has said, and he's, by the way, also the head of the Mars rover project, the Spirit and Opportunity rovers for NASA. He has said that in the long time that the Mars rovers have been on Mars, they've made great discoveries, but just he himself, in a half an hour, could have done much more.
Right.
And that's not a boast on his part.
No, it's just the fact of being a tactile, observant. It's like trying to get a computer program to understand what a pizza is.
Yes. So
we get it immediately.
So I think that the interesting opportunity that exploration affords us is also in the area of discovery. It's also in the area of making money. So there's probably something in it for everyone with regard to space. What I'll tell you I don't think is the reason to go to space is I don't think we should be abandoning Earth to try to find a better planet to live, or to give up on the Earth because of global climate change to try to find a better place to live on Mars.
Right.
I don't think that backing up our species in space is really necessarily the reason we should be doing this. I think it's not an either or. I don't think we're going to be doing Earth or Earth 2.0. I think it's an and. Right. I think extending our presence out into the solar system is a natural evolution, just the way our ancestors came out of Africa at one point. We will all, at some point, benefit from being a spacefaring species.
Thank you so much for coming. We've had such a great time, but we are out of time. That's one thing that is a constant in television.
Well, it's been a pleasure.